Hi everyone, welcome to the second part of data analysis. In this video, we're going to dive into three important topics. First, we'll explore what exploratory data analysis is all about. Then we'll look at how to evaluate and explain the results of data analysis. And finally, we'll talk about the role of artificial intelligence and machine learning in today's data-driven world. Let's get started. Let's begin with exploratory data analysis, or EDA for short. Think of EDA as the stage where we really get to know our data before we jump into modeling or drawing conclusions. We're asking, what's going on here? What patterns can we find? What might need a closer look? In EDA, we start by using descriptive and diagnostic techniques like summary stats and visual tools to understand trends and catch anything that looks off. The main goals of EDA are to understand how the data is structured and how clean it is, spot missing values or errors, examine how variables behave and interact, uncover relationships, trends, clusters, or seasonal effects, and generate ideas for future steps, like which variables we might use in a model or what transformations we might need. This stage sets the foundation for all the analysis that comes next. One of the key things we look for in EDA is how variables relate to each other. We may use either the numerical statistics or visualizations. We often start with correlation, which tells us how two numeric variables move together. A correlation value ranges from -1 to 1. A value close to 1 means a strong positive relationship, while a value near -1 shows a strong negative relationship. A correlation of 0 simply means no linear association. So if we think customer income and spending are related and the correlation is 0.75, well, that supports our hunch the two variables are strongly related and move in the same direction. Another method is cross-tabulation, which helps us explore relationships between categorical variables. For instance, if you survey customers on their shopping preferences and age group, you can build a table to see how many people in each age group prefer online versus in-store shopping. You'll quickly see patterns like younger people preferring online and older ones favoring in-store. And then there's the scatter plot, a visual tool for spotting patterns between two numeric variables. In the scatter plot, each point on the chart represents one observation in the dataset, with one variable being plotted on the x-axis and the other on the y-axis. Imagine plotting gym members by hours exercised per week versus weight lost. The points show an upward trend from left to right-hand side that tells you more exercise is linked to more weight loss. Now let's talk about data drilling. This is where we zoom in on our data. Data drilling lets us start from a high-level summary, then dig deeper to understand what's driving those numbers. For example, we might begin by looking at total sales by region. Then we drill down into sales by state, then by city, and even by individual store. Data drilling helps us investigate trends or anomalies. If something looks unusual at the top level, you can drill down to find out what's really going on underneath. Helps us identify root causes of issues. Whether it's a drop in performance or a sudden spike, drilling helps pinpoint which segment, group, or variable is responsible. Helps us compare performance across different levels. You can easily compare how specific categories, like departments or product lines, are contributing to the overall picture and helps us support data-driven decisions. With more detailed insights, you're better equipped to make informed, targeted decisions instead of guessing. The level of detail in your data is called its granularity. For example, you might have data recorded once per year, once per day, or even every second. If the data is at the yearly level, that's called low granularity because it's more general. If it's recorded by the second, that's high granularity because the detail is much more precise. So the finer the detail, the higher the granularity. The more general the data, the lower the granularity. EDA also uses data mining techniques to find deeper patterns in large data sets. For example, they help us spot outliers, anomalies, patterns, and correlations. Outliers are individual data points that stand out. They're either much higher or much lower than most of the other values. For example, if most people in your dataset earn between $40,000 and $100,000, but one person earns $5 million, that's clearly an outlier. Outliers can sometimes lead to misleading conclusions. They might indicate a data entry error, a rare or special case, or even something worth investigating further. Data mining helps us flag these unusual values so we can decide whether to keep them, fix them, or analyze them more closely. Anomalies are a bit different. Instead of just a single extreme value, an anomaly is an unusual or unexpected pattern in the data, often involving multiple variables or behaviors. For example, if your website traffic drops suddenly across all regions on a single day, that could be an anomaly. It might mean a system failure, a tracking issue, or even a cyber attack. Anomalies are especially important in machine learning, fraud detection, and system monitoring. Remember, outliers are individual extreme values. Anomalies are broader, unexpected behaviors or patterns. Patterns are regular trends or behaviors in the data. They help us understand how different variables are related. For example, if customers who buy bread also tend to buy butter, that's a buying pattern. Recognizing patterns is helpful in areas like marketing, recommendation systems, and behavior analysis. Data mining helps uncover these patterns so we can make smarter predictions and decisions. Correlation tells us how two numeric variables move together. A positive correlation means as one variable goes up, so does the other. Example: more study time usually leads to higher test scores. A negative correlation means as one goes up, the other goes down. Example: as price increases, quantity sold usually decreases. But one important note, correlation doesn't mean causation. Just because two things move together doesn't mean one causes the other. Still, correlations are very useful for exploring relationships and building predictive models. Besides using mining techniques, we also use box plots to spot outliers visually. A box plot shows the 5-number summary: minimum, first quartile, median, third quartile, and maximum. To detect outliers, we calculate boundaries using 1.5 times the interquartile range. Values beyond those are flagged as outliers. On the chart, you'll see outliers marked with symbols like asterisks. Box plots are especially helpful for quickly checking distribution and spotting any extreme points in the data. After we run our analysis, the real challenge is interpreting the results clearly. First, let's talk about trends. Trends show whether something is rising, falling, or staying stable over time, like monthly sales or website visits. We use charts, moving averages, or regression lines to help visualize those patterns. Next is expected value. This is the average outcome based on probabilities. It is calculated by the summation of the products between each possible value and the corresponding probability. For instance, if you have a 30% chance of selling 100 units and a 70% chance of selling 200 units, your expected value is 0.3 times 100 plus 0.7 times 200, and that is 170 units. Then we interpret model results, say from a regression or classification models. We look at R-squared to see how well the model fits the data, look at the coefficients to understand how each variable influences the outcome, and look at the residuals to check the difference between predictions and reality. A good example of interpreting the predictive models is that a linear regression model predicting housing prices finds that square footage and location significantly increase price while the age of the house decreases it. All of this helps turn numbers into insights and ultimately into smarter decisions. A p-value helps us decide whether the results we see are likely just due to random chance or if they suggest a real effect. If the p-value is low, usually less than 0.05, that means the result is unlikely to be random. We say it's statistically significant, and we reject the null hypothesis, which is the idea that there's no effect. But if the p-value is higher than or equal to 0.05, the evidence isn't strong enough and we fail to reject the null hypothesis. For example, suppose a new drug is being tested against a placebo and the p-value comes out to 0.02. That's below 0.05, so we'd say the drug has a statistically significant effect. A t-test compares the means of two groups to see if they're significantly different. It helps answer the question, is this difference real or just random variation? After running a t-test, we get a test score and a p-value, which tells us whether the result is significant. Let's say we're comparing average test scores between students who studied online versus in person. If the p-value is less than 0.05, we'd say the difference is statistically significant. If it's 0.05 or higher, we'd say there's no significant difference. Regression analysis is used to model the relationship between one dependent variable and one or more independent variables, like education level or age. Regression helps us with two big goals: explaining how different factors affect an outcome and predicting future values based on input variables. After we run a regression, we usually focus on three things: coefficients. These tell us how much the outcome changes when the input changes. R-squared, this tells us how well the model explains the data. P-values for each variable, these tell us which predictors are statistically significant. Once we've run our test or model, it's important to translate the numbers into plain language. Here's how to do that effectively. Explain what the result means in a way that a non-statistician can understand. Use visuals like charts or graphs to tell the story. Connect the results to decisions. What action does this support? And if needed, mention any limitations, like small sample size or assumptions that may not fully hold. Now let's shift gears and talk about artificial intelligence, AI, and how it supports data analysis. AI refers to the ability of machines or computer systems to perform tasks that usually require human intelligence, like recognizing patterns, learning from experience, making decisions, or even understanding language. In the context of data analysis, AI helps us handle large, complex data sets faster and smarter. It can automate repetitive tasks, spot patterns we might miss, and make decisions based on data. Imagine trying to read through millions of customer reviews. AI can scan all of them in minutes and highlight common themes like frequent complaints about delivery delays way faster than any human team could. Machine learning, ML, is a subset of AI. It refers to systems that can learn from data, which means they get better over time without needing to be explicitly programmed again and again. Instead of telling a computer exactly what to do, we give it data and the system figures out patterns or solutions by itself. There are two types of main machine learnings. The first one is the supervised learning, which means that the model is trained on data that includes both the inputs and the correct outputs. We call this labeled data. The common tasks are classification for categorical data and regression for predicting continuous values. The popular approaches include linear regression, logistic regression, decision trees, random forests, support vector machines, k-nearest neighbors, and neural networks. The second one is unsupervised learning, which builds the model on unlabeled data and must find patterns, structures, or groupings in the data without any predefined labels. The goal is to discover hidden structures or group similar observations. Popular unsupervised approaches are k-means clustering, hierarchical clustering, principal component analysis. An algorithm is simply a set of instructions or rules that a computer follows to solve a problem or complete a task. AI transforms data analysis in many ways. For example, in pattern recognition, AI detects patterns in large datasets, such as identifying sales trends or customer behavior patterns across thousands of transactions. In prediction, AI models can forecast future outcomes, like predicting customer churn, product demand, or stock price changes. In automation, AI can automate tasks such as data cleaning, error detection, and report generation, saving time and reducing human error. In personalization, AI enables customized recommendations. For example, Netflix suggesting movies based on your viewing history. And in real-time analysis, AI systems can monitor data streams in real time. For example, fraud detection in banking systems or traffic monitoring. All of these make our work faster, smarter, and more scalable. Machine learning approaches also play a major role in how we analyze and act on data. In classification, they help sort items into categories, for example, classifying emails as spam or not spam. In regression, they help predict numeric values, for example, forecasting next month's sales. In clustering, they find natural groupings in the data, for example, grouping customers by purchase behavior. In anomaly detection, they spot unusual values or patterns, for example, identifying fraudulent credit card transactions. In dimensionality reduction, they simplify datasets with many variables while keeping the most important features, for example, summarizing survey results with many questions. Each of these tools helps us uncover insights and take action more effectively. Let's wrap things up. In this video, we covered exploratory data analysis, how we explore data structure, quality, and relationships. We also discussed how to evaluate and explain results using trends, expected values, statistical models, and p-values. Finally, we explored how AI and machine learning help us scale our analysis, make predictions, and automate decision-making.